Live on YouTube now. All right. Live on YouTube now. All right. Okay. All right, guys, so I'm going to go ahead and get started here. It's 1:02. We have quite a lot to get through today. So as I mentioned the last time, we've been focusing on electrochemistry for this first week. So we're doing classes for 2 weeks in March, 2 Sundays in March. And today I wanted to focus on electrochemistry. And so electrochemistry, there are different levels to it. So like first you have just like definitions, ground rule, make sure that we're all on the same page about what the different concepts are, what the definitions are. Then after that, now we can go into the electrochemical series and how ions discharge, what gets preferentially discharged. And then of course, calculations, which I want to spend the bulk of the time on. And then of course there are applications and examples that would be worth your while to know, just in case those pop up on the exam. But I think it's good to lay the framework, have a good foundation, and then have a lot of practice with the problems, right? Because there are different kinds of problems too, right? Which really test your understanding of it. So let's just jump into it and start by focusing on the fundamentals, and then we can hopefully we'll get to do at least a couple questions today. So let's see, I'm gonna share my screen now with what I have prepared for today. So let me start from here. Okay. So welcome again. Thank you guys for sticking this out and remembering that we have class today. So thank you guys for coming. As I mentioned, now we're in March. We have 2 formal lectures left to go. And then in April, I'll be doing some past paper marathons, and I'll give you guys more information about that and what the price associated with that would be. It won't be anything exorbitant, because I know that you're all students just trying to make your way in the world. But because of the work that's involved in that, I'll definitely charge a small fee. I think that that's fair. So I'll let you guys know about that. But as far as March goes, we only have 2 classes. The first of which is today, March 13th. And so this is electrolysis, electrochemistry more broadly, right? So the actual topic that we're focusing on is electrolysis. And let's see. If you think of the word electrolysis, right? What comes to mind? When you break up those 2 words, what do you get the sense of what's happening here? Like I generally, if I'm like completely lost with something, right, and I kind of know nothing about it, I try to like break up the words to see if that could point me to some general sense as to what might be going on in this particular case. So when you see electrolysis, what comes to mind? Like, what do those 2 words mean that they didn't put together? Electricity, Claude says electricity. Akeen says electricity. Am I pronouncing your name correctly, Akeen? Is it Akeen or is it Akini?
Akini, miss.
Akini.
Yes, miss.
All right, got it. So you guys say electricity, very good. So the first part of that word is stemmed from electricity. And then the last part, which means lysis. Lysis means like to break up something, or lyse. To lyse something means to break it up or like deteriorate it, decompose it, right? So when we put the 2 things together now, what we're saying is we're using electricity or an electric current or something that can carry electricity to decompose something, or throughout the process, there's some way in which electricity is going to cause a decomposition of whatever it is that you have, right? In this particular case, largely these are solutions that we are breaking down by passing an electric current through it, right? So when you look at those 2 words together now, you always remember, right? Just look at the word and you're like, okay, electrolysis, we're breaking down things using electric current, right? Okay, so to get started, as I mentioned earlier, so if we look at the bottom box here, electrolyte is from a formal definition standpoint, is really a chemical change which occurs when electric current is passed through an electrolyte. So if you have an electrolyte, which we'll get into more details as to how we define that later, if you have an electric current and you pass it through that electrolyte, right, a chemical change will then occur. And that chemical change, that whole process we call electrolysis. So we're breaking down this electrolyte by passing an electric current through that solution, okay? So just to back up a little bit, then we have this idea of conductors versus insulators, which we're all very familiar with from our kids, right? That you have things that conduct and things that are insulators. And for intents and purposes of what we're focusing on today, when we talk about electrical conductors, we think of things that allow electricity to pass through them, right? They're not resistant to that flow of electricity, so they allow electricity to flow through them. And when we think of our conductors, we have metals are very good conductors of electricity. So we have those, and then we also have or insulators, which we're all very familiar with too. We have wood. We know that wood doesn't conduct electricity, doesn't conduct anything really. We have, wait, go ahead.
Graphite.
Graphite is a very good, what is that? Conductor or insulator?
Conductor.
Very good conductor. Give me another good conductor. You have any more off the top of your head that you remember?
Copper.
Copper, because copper is a metal, yeah, so that's great. And then as far as insulators go, we have wood. I just threw out wood. Do you have any other examples of things that are, what they are really is they're resistant to electricity flowing through them. They don't allow electricity to flow through them. They're like, nope, you can't come through here. So are there any other examples that you can think of? Let's see, somebody wrote something in the chat. The human body is a conductor. Yeah, that's solid, Paige. That's a very solid answer, because we do have ions through our body, right? So we can conduct, right? If when you have people get electrocuted, right? That's because they're ions that then get, you know, associated with whatever is like passing through. People get electrocuted quite a lot, actually. Well, let me not say a lot, but it happens, right? And it's because we have ions in our bodies too that can current. Diamond is an insulator, Jada says. Yes, so that works. Wait, go ahead.
Crystals. Crystals, one of them.
Crystals, so yeah, so your ionic crystals, right, can conduct. But the ionic crystals, what has to happen for them first, Aquila? Like in their native state, they're not gonna conduct. Something has to happen for them to be able to conduct. Do you remember?
I think it was one of the two of the ions them. I think when the two of the ions them held together. I don't remember.
So like, okay, so let me follow you along that line. So like, for example, a very popular ionic crystal or crystal that we talk about is sodium chloride, right? So like sodium chloride is an ionic crystal. It forms this very intricate 3D lattice structure. You might remember that back from like fourth form stuff. And so when it forms that lattice structure, it's very rigid and the particles are like close together. But if it's in a molten state, right? So you kind of melting it now. So it's in a molten state and you get to like free up those ions, which are the particles that carry the electricity, then it can then conduct. Or as Jada said here, Jada says you have to either dissolve them or separate them. So the separation part, well, they're separated in both cases where you have them in a molten state by melting them and the ions come apart, or you have the case in which you're dissolving it in a solvent like water, and that frees up the ions as well. And so that's a very important point that we just raised, because as we delve deeper into electrolysis, you'll see that there's a difference in when you have a molten solution. So say molten sodium chloride, versus sodium chloride in aqueous solution where it's dissolved in water. Because as I mentioned earlier, when we talk about electricity or electric current flowing, it's really the flow of charged particles, right? So it's the flow of ions, it's the flow of electrons, and that's how we get the electric current flowing, right? So just remember that now that we're going to come back to that idea of how you have a molten, you can have molten sodium chloride or aqueous sodium chloride, and the way that electrolysis proceeds in both those cases is very different, right? Because of the charged species that are available. So just to bring it back around, if you have an ionic crystal, that's just in its native state and it's just fixed. Like if you have salt, like a block of salt in your kitchen by itself, just the block of salt, it's not going to conduct electricity. It needs to either be molten or dissolved in water, so you have those ions getting freed up, right? So just think of, when you think of conductor, just think of that, like, does it have anything that can flow? So that means, does it have charged particles like ions or electrons that are mobile? So, okay, it can have the charged particles, but are they mobile? Can they move? Because they have to be able to move, right? For that electricity, for that conduction to take place. It has to be mobile. So think of that. You can have charged particles, but can't do a thing because the charges are, the charged species are fixed. They can't move, okay? So just keep that in mind when you think about conduction. And insulators, of course, the insulators don't have a thing in them. They can't conduct anything. They're just like, they're fixed, right? So like plastic doesn't have any charged particles in it, so it can't conduct anything, right? So just keep that in mind. And then now, we kind of touched on this just now when we were talking about what are conductors, right? So under conductors, we have two broad classes of conductors. We have metallic conductors and we have electrolytic conductors, right? And so from a metallic standpoint, it's important for us to remember, like, as we're going forward and as we're building this foundation in chemistry as a whole, what I've been emphasizing in my one-on-one sessions with students, I have some fourth formers who are just starting out in chemistry, right? And what I'm emphasizing really is this idea that as you're building a foundation, you have to be paying attention to things like the structure of matter, whatever the matter might be a metal. So pay attention to that structure. And so how is it structured? How are metals structured? Metal is a solid, right? So you know that the particles are closely packed. They just have like room for vibrational motion. They're not going to be moving, making like big oscillations like liquids and gases. They're like kind of fixed, right? So you have to kind of use that knowledge of the structure and see how that informs the function or the behavior of that matter. So in this particular case, let's look at metal. So we're saying here that we have metallic conduction and we have electrolytic conduction. Those are the two broad classes, right? So from a metallic conduction standpoint, if you remember back to when you were doing metallic bonding, right? We spoke about, well, I didn't really teach you this because I'm just getting to know you guys and starting with you. But when you learned this in fourth form, you might remember, and correct me if I'm wrong. So like raise your hand and let me know if you learned this. But as far as metals go, right, when you think about metallic bonding, really what you were taught is that metallic bonding arises when there are these delocalized electrons. So there's like a, what would they say? They're like positive ions or cations in a sea of delocalized electrons, right? So you have your metal atom, right? And that metal atom loses that valence electron. So now it's positively charged, right? You lose an electron, you have more protons. So the overall charge, that atom now becomes an ion, a positive ion, that's known as a cation. And then you have your electrons just floating around, the electrons that were lost. So you have your positive, you have your cations in a sea of delocalized electrons. So the electrons are running around. And so that's pretty much how that metallic structure is, right? You have your positive cation, and you have the electrons floating around, and because positive and negative attract, you're able to have that network, kind of like a lattice structure again of metals, right? So if you're following along with that, please let me know. Raise your hand and let me know if that concept is clear to you, because that comes into this whole idea of conduction, right? So raise your hand or give me a thumbs up and let me know that that's clear to you, and I can continue along those lines, right? So okay, so we just established that we have our positive ions, also known as cations, and these are in a sea of delocalized electron, right? So then the idea then, as I mentioned earlier, for conduction, you need charged particles, so ions or electrons that can conduct that, that can carry that electric current, right? That's really where the electric current arises from, is those charged particles. So you can see how from the standpoint that we have metals being able to conduct because they have the delocalized or the mobile electrons that can move, right? And that's very important to note. When we say delocalized, just think of this. Always think back as to what the wording actually means. So if it's delocalized, it means that it's not fixed in any one space. It's not local to any one thing. It can move around. So that's the basis of metallic conduction, right? And then we have electrolytic conduction, which is where we have our electrolytes having electricity flowing through them, right? So let's talk about electrolytes for a little bit now. We have strong electrolytes and we have weak electrolytes. But before we start to talk about the strength of the particular electrolytes, can anybody tell me in their own words what an electrolyte is? Like what's an electrolyte? And remember earlier, I said electrolysis is when you have an electric current that breaks down a compound. There's a chemical change that occurs in that compound when you apply the electric current through it. So what's an electrolyte? What would you define as an electrolyte? Anybody, feel free to share that with me. What is an electrolyte?
A substance that conducts electric current.
Exactly. So it conducts electric current. And what is the basis of that conduction? What are the charged particles here that are moving in an electrolyte? Is it electrons? Is it ions? Is it like, what is the basis of the conduction?
Is it ion?
It's the ions, right? So it's the ions that are carrying the electric current in this particular case. So it's the movement of the ions in this liquid or in this solution. And that's as a result of the application of what they call a potential difference or voltage, right? Which essentially translates to current. So it's coming from that physics concept of a potential difference, right? But don't worry about that too much. Just know that you have to apply that potential difference to your solution. So I have some water here, which we can touch on later, but water isn't really a strong electrolyte. It's a weak electrolyte. But I have this here, and like when it's like this, just in this cup, it's not going to conduct electricity. There needs to be a potential difference. I'm going to need to hook this up to some wiring, right? Like you've probably seen in your textbooks where you have like something coming out here, something coming out here, which we'll touch on later, and we call those electrodes, right? And across that, you're able to develop a potential difference. But like this, it's not going to conduct, right? So keep that in mind. So electrolytes are able to conduct electricity through the movement of ions, right? Movement of the ions that are in this when you apply a potential difference. You have to remember that part. When you apply a potential difference, if there's no potential difference, nothing is going to happen. This water, I can drink it right now. Nothing is going to happen. There's no electricity flowing through it, right? So keep that in mind. You need a potential difference for the electrolytic conduction, for conduction to take place, period, right? Okay, so those are electrolytes. There are a bunch of them. There are a bunch of different electrolytes. You have your acids are strong electrolytes. I think we did acid, bases, and salts. I'm not sure if we touched on that here, but like you have strong electrolytes and you have weak electrolytes, right? So strong electrolytes, it means that when that electrolyte is completely ionized, right? Say for example, what would I say?
Ammonium.
it's completely ionized. It's not partially ionized. Like all the ions are freed up when you dissolve it. So if it is that you're dissolving, so if we go back to our ionic crystals example, Aquila, we were saying how, say you have sodium chloride and you dissolve sodium chloride in water, all of those ions are free and liberated. So in that solution now, after you dissolve it, you have a high concentration of ions. And because you have a high concentration of ions, and ions are what cause the conduction and the flow of electricity, then we're good. That's very good. It's strong because there are lots of ions that are liberated. It's fully ionized, right? A weak electrolyte, it's only partially ionized. It's like partial ionization. So it's not as effective at conducting electricity. It can, but it's not going to be as strong as if we had something, an electrolyte that every single ion was now free to move, right? Because we need that mobility for the electric current to be conducted sufficiently. So the distinction between strong and weak is that the strong one is fully ionized. So all the ions are free to roam about and have fun. The weak ones, it's only partially ionized, so only some of them. So that would be a low concentration then of ions, right? Strong electrolyte, fully ionized, high concentration of ions, and that's what we want. That's what we would prefer, right? We have no control over whether an electrolyte is weak or strong. It is what it is, right? So for example, water I mentioned earlier, water is a weak electrolyte. Like I was looking at some numbers and it said that in every 560 million water molecules, like imagine you have 560 million water molecules and only one of those is ionized, gets ionized. Like only one out of the 560 million. So water, like if I were to like hook this up, right, to like current, it's not gonna do much. It might carry a little bit because one out of the 560 million is ionized, but it's not gonna be anything massive. And so I wish I had my setup to show you guys here, but essentially, if you have your electrolytic cell, which we'll touch on a bit from this, when you have your electrolytic cell, if you have a strong electrolyte and you put a light bulb, so you have your solution like this, and you set it up, and you have a light bulb at some way throughout the circuit, you have a light bulb, right? At some point, if it's weak, the light bulb is just gonna only like be dimly lit. If it's strong, the light bulb is gonna be very bright, right? So you're using the solution to create that, to drive that electric current because of the mobile particles that are in the solution. So if it's not enough, because it's weak and it's partially ionized, the bulb that's in your circuit is gonna be dim. And if it's strong, there are lots of ions. They can conduct the electricity. The light bulb is gonna be bright. So just keep that in mind. So let's see now where we are. All right. So now maybe I should advance. Yeah, so let me advance so I can talk it through from here. So this is what I was referring to just now when I was saying how we have a little circuitry going on, right? We have a battery here, and the battery is what provides the potential difference that I was saying that we need. We need a potential difference. It's not enough to just have an electrolyte, a substance that has ions that could potentially become mobile. There has to be a potential difference applied that will move those ions, right? Move those ions around, be able to move them from point A to point B, right? So as I mentioned earlier, electrolysis is the decomposition of a compound by an electric current. So you have an electric current that arises from the potential difference. And when we have our thing and we put the electric current through it, if it's if it has ions in it, it gets those ions are the electrolyte is broken down into those constituent compounds, right? Constituent charged particles, right? Those are free to move, and so when you apply that electric current, right? So that's electrolysis. And so here I am showing you what we refer to as an electrolytic cell, right? So it's the cell in which the electrolysis takes place, or we can also call it electrochemical cell, right? Because I mentioned earlier, it's an electrochemical reaction, so to speak, that happens, right? We have the electricity that's causing a chemical change. So it's an electrochemical cell, or we can also call it an electrolytic cell, okay? All right, so follow me along here, and I'm gonna walk you through it and walk you through the components, just kind of talk through it so you can kind of see the different components that make it up. And this will be very important as we advance and as we move forward, because you need to know what these things are, because the questions, the electrolysis calculations hinge on you knowing these things. If you don't know anything about this cell, you won't be able to answer any question. You just be making it up and being like, oh gosh, I don't know. I really don't know. We don't want that. We want you to know the things going in, so you know what you're doing and why you're doing it. So if you weren't paying attention before, I definitely say pay attention right now as I'm walking and talking through this electrolytic cell, electrochemical cell setup, okay? All right, so let's start. Let me start with our electrolyte, because we all know what electrolytes are. I just told you what it is, right? It is that solution that has these charged ions in it that are capable of then carrying that electric current, right? So in this particular case, let me get my pen, because I'm gonna mark stuff up to really emphasize things so you can see what's really going on here. So we have our molten NaCl. In this particular case, this is our electrolyte, right? So we just write that over here. So this is our electrolyte. We're all on the same page as to what an electrolyte is. This is our electrolyte. This is the thing that it's in the molten state now, Aquila. As I said, it had to be in a molten state or a dissolved state for it to be able to carry that electric current. So it's in a molten state here. So it can, the charged particles are mobile. So you see we have our sodium ion that came from here, and we have our chloride ion that came from here. All right. So now we have this sodium ion, and that sodium ion is a positively charged ion. It's also what we call a cation, right? Let me know if we're all on the same page. Give me your thumbs up as we're working through this so I know that nobody's getting left behind, right? All right, so we have our chloride ion as well, and that comes from our molten NaCl. We have our chloride ion, and that is an anion. That's what we call negatively charged species. We call them anions, and we call the positively charged species cation. Look at this now. I just said that we call our positively charged species cation, and we call our negatively charged species anions, right? All right. So the key, a very integral component of an electrolysis cell is what we call these electrodes, right? And the electrodes are these regions in the electrolytic cell to which the ions are attracted or drift towards depending on their charge, depending on the charge of the ions that are in the electrolyte, right? So the electrodes are where the charged ions migrate towards, depending on their charge, right? So I said the chloride ion is negatively charged. It's an anion. And so what happens is, because it's negatively charged and it's an anion, it goes towards what we call an anode, right? So anions go towards the anode. The cations, which are the positively charged species, they go towards the cathode, right? As I mentioned earlier, these electrodes, they have a charge associated with them themselves, right? So if I am saying that the chloride particle is an anion and it goes towards the anode, what does that tell you about the charge of the anode, right? We have a negatively charged species, the anion, and it's going towards the anode. What is the charge of the anode? And similarly, what is the charge of the cathode? If we have positive species flocking towards it, what does that mean about this, the character from a charge perspective of the cathode and the anode? So somebody tell me that. What's the charge on each?
It means the anode is negatively charged and the cathode is positively charged.
Repeat that again and talk me through how you arrived at that.
Oh, okay. So you said the anions go towards the anode, right?
Yeah.
They're attracted to it.
Yeah.
Okay, so the anode is positively charged.
Exactly. That's exactly right.
Yes, that is it. It catch my off guard too, you know, miss.
Yeah.
It's like an opposite. You know, like we just are the Na plus is positive, but yet still it's can't explain it. But yeah, there's a twist to it. Doesn't make it. Because that's the same thing with the SBA, yeah.
But is it clearer now though? Can you kind of see? I get what you're saying about it being tricky. But you have to think of it from the standpoint of anions are negatively charged, they're going towards the anode, right? If it's negatively charged, it's not going to go towards something that's negatively charged. So if it's going towards anything, that thing has to be positively charged.
Yeah, yes, Mr. I messed up the first time.
Yeah, maybe it's a name that is throwing you off because it's an anode. So you're like, oh, but anode, anion, negative, they're all negative. No, the anion is negative and the anion is going towards the anode. But it's going towards the anode because the anode is positive. It's the opposite charge from it, right? And then similarly, the cathode, you have cations. Cations are positive and they're going towards the cathode. If I'm positive, I want something that's negative. Opposites attract. So if I am a cation and I'm going towards the cathode, it means that the cathode is negative. It has to like balance me. We're opposite and we attract because we're opposite. I'm positive, you're negative, I want to come to you. I am a cation and I'm going towards the cathode. That means that the cathode is negative. Does that make sense?
Yes, miss.
Okay, so let me write. I want to put that in black. I have it in pink, but it's kind of hard to see, at least from my end. So let me see if I can write that charge over again. So this is my negative, right? Let me just write it negative, and then this is positive. Guys, it's very important, you know, that we're all on the same page here, because it's gonna get more complicated. But are we all on the same page here?
Yeah, yes,
So what is what? Okay, let me see those thumbs up. Ashani, you're talking, right?
Yeah, yes, miss, it's me.
Okay, all right, so just give me those thumbs up so I can see that we're all on the same page. All right, very good. All right, so okay, so we know what the anode is now. We know what the cathode is, right? And as I said, those are electrodes. That's where the ions in your electrolyte are gonna move towards, depending on what the charge is, right? So we're all good on that. Those are electrodes. Okay, so let's talk about so just now we spoke about the charge of the electrode and saying how one is positive and that's the anode and one is negative and that's the cathode, right? But from a chemical standpoint as to what actually makes up the electrode, on that basis, we can speak about two classes of electrodes. And so those classes are inert. So you have inert electrode. So you notice that these are inert. So you have inert electrode and you have active, right? Does anybody know what the difference is between these two words? Like what do the names suggest? If one is active and one is inert, what's the one that's inert? What does inert mean?
I'm going to use a context clue and say it means it's dormant or something.
Exactly. That's exactly how you approach this. Who was that? Who said that?
It's Ashani, miss.
Ashani. So that's exactly right. So it's inactive. Ooh. So it's
Well,
inactive. He said it's based on the context clues. He's like, it's inactive. It means that it's inactive. If we're saying that the other one is active, and there are two broad classes, and I'm saying that one is active, it means that the other one, with that fancy word inert, it just means that it's inactive, right? So you have your active electrode and you have your inactive electrode. And what that means for us is that if it's active, it means that the chemicals or the composition is going to affect the electrochemical reaction. And we'll get to that right after this when we talk about this idea of an electrochemical series. But if it's active, it takes potentially, it could potentially take part in the electrochemical reaction, right? But if it's inert, it's not gonna affect anything. And oftentimes, to avoid any complication, people will just use inert electrodes, right? So you know it's inactive, it's not gonna compete with anything, it's just gonna be there, and whatever happens, happens. It's just as a result of the electrolyte species themselves that are gonna affect the reaction, the electrochemical reaction, and not the electrode. The electrode is not gonna participate in it at all from a reaction standpoint. So are we clear on that? That the difference between inert versus active? Thumbs up and let me know if that's clear, because that's very important, right? So this is somebody's asking why it's not active. It's the what makes it up. It's inactive species that make it up. So like let me give you an example. For the inactive electrodes, you would use like insulators, right? So you would use, let me tell you, so you have like graphite, that's a carbon-based one that's inert, and you have platinum. So platinum and graphite electrodes are general. Let me write that down, the inert one. So like if you start a problem and you see straight up, and they will tell you this in the problem, they'll tell you straight up what the electrode is made up of, and the inert ones are platinum. So I'm just gonna write PT, which is the symbol for platinum, and then carbon, and the form of carbon is the graphite, right? And that's inert. It's not gonna take place in the reaction, but if you ever see that the question is telling you that you have a copper electrode, you have to be on the alert and pay attention to what's gonna happen. And I don't know what time is it, 1:40? Hopefully we'll have time so I can actually show you an example of how copper can mess up what's going on in your reaction, right? So if the question tells you right from the jump that it's an inert electrode, or it might not even say inert, it might just say it's a platinum electrode or a graphite electrode, it means that those electrodes are dormant, they are inactive. But if the question says that you have a copper electrode, in the midst of everything else that they're telling you that question, you have to sit down and really think twice before you proceed with writing any half reactions or half equations, right? So that's kind of where we're going next, this idea of this half equation that you very often, you have to start there when you're doing the electrolytic calculation. So are we on the same page, guys? Are you clear on that? That's why it's important for you to know that they're inert and active electrodes, because like this is important, right? As we build up to the calculations. So is that clear to you guys? Pay attention. Long and short of it is, pay attention to copper electrodes, right? If it's a copper electrode, open your eyes wide like this and really pay attention. Let me see what else I wanted to touch on here. Okay, so from physics, you probably are aware that the electricity or the electrons flow from the anode to the cathode. So it goes from the positive end to the negative end. So that's why you see these arrows with these electrons are going around like this. It's coming from the positive and it's flowing in this end and going around to the negative, right? So that's how electricity flows from positive to negative. So jot that in your notebook somewhere too. Electron flow from positive to negative. All right. Okay. So last time we touched on, that's why I really wanted to touch oxidation and reduction with you guys last time. Last time we touched on those ideas or that concept of oxidation versus reduction. Can somebody remind me of what is oxidation versus what is reduction? And there are different definitions for each. So, okay, oxidation, you can define oxidation in, I think I taught you 3 different ways. Does anybody remember those 3 different ways that you can define oxidation? And then reduction as well?
I wasn't.
Yeah, just shout out one. Shout it out.
Oxidation is the loss of electron, and reduction is the gain of electron.
Yeah,
Oxidation
okay.
is the gain of oxygen, and reduction is the loss of oxygen.
And then finally,
I wasn't present back then, miss, but I remember. I know.
The oxidation number increase and reduction number decrease.
Exactly, that's exactly right. So who is it that was saying, who wanted to say something as well?
I was leaving, Mr. Ashan. I was saying I wasn't present, but I know this oil rig thing.
Okay, yeah. So oil rig is very important to remember. Like that's the key thing. And I think when I was teaching you guys the oxidation reduction stuff, I was saying how I think that's the most important definition is the oil thing for you to remember is the oil rig, because ultimately you're gonna have cases in which you don't necessarily have any oxygen in your equation, like here, right? I'm gonna show you oxidation and reduction in this particular system that we're working with here. And as you see, there are no oxygens in it, right? So if you were solely relying on that definition about addition of oxygen versus removal of oxygen, you would be lost, right? So for most cases, the electron transfer definition, which is this, where's my pen? Okay, so it's this, oil rig is best. And that's the one that if you don't know, if you don't remember anything else about oxidation and reduction, you have to remember that oxidation is loss of electrons. Loss of E, and then the reduction is the gain of E, right? So always remember that, because that's the definition in terms of electron transfer, and that's what we're working on. We're doing electrochemistry. We care about electrons, what is going on from an electron transfer standpoint. So always remember, oxidation is loss, reduction is gain. All right. So let me know if we're on the same page, because I'm going to bring it up a notch now. So are we all clear on that? How we're defining oxidation and how we're defining reduction? Give me those thumbs up and let me know as I add on another layer of complexity right now. So let me know if that's good for everyone. I can't see the thing. Let me see. Okay. Show me those thumbs up before I move on, so I know that I'm not leaving anybody behind. Okay, I see the thumbs up. That's good, 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 good. All right, so here we go now. Adding on another layer of complexity now. We're building up, right? So I'm gonna clear off what do I want to clear what I have on the screen? No, I'm gonna find a corner to write in. Hopefully it's not confusing to you guys. Hopefully you're still following with everything that's on the screen. I was gonna clear it so I have more room, but I don't want to do that because I don't want to have to like write it all over again if I have to re-explain something. So I'm gonna find a little corner to write in, and maybe I'll just write under here actually for where the definitions are, as I show you how oxidation reaction is actually taking place and why and how you can remember it as easily as possible. So let me get my pencil back. Let me see what color I can use to contrast that. I'm gonna use this. No, let me use white. I'm gonna use white since I'm writing in there. Okay. All right. So the anode now, as a general rule, what we're saying is that this oxidation that we spoke about earlier, which is the loss of electrons, takes place at the anode, right? The anode is our positively charged electrode, and the anode is where the anions migrate towards, right? Anions are negative, the anode is positive, the anions are wanting to go towards the anode, and when they reach the anode, they will be oxidized. They will lose their electrons, right? Give me a thumbs up if that's clear. The anion is going towards the anode, which is positively charged. At the anode, oxidation takes place. When the negative anion, the anion gets there, it's going to lose its electrons. That's what we mean. All right. So our anion of interest here is chloride. Let me just say the chloride anion, right? So we have Cl minus, right? That's our anion. It is now at the anode. It is gonna lose its electron. So let's think about it for a minute. This chloride ion is an ion, which means that it was previously an atom, right? How does an atom becomes negatively charged? How do you get an ion from a neutral atom? If I have a neutral atom, that means that the number of protons and electrons are the same. Like there's no one is overpowering anybody, right? So you're neutral, you don't have any charge, right? If it becomes a negatively charged ion or an anion, it means that now you have more negatively charged species, i.e. your electron, than proton, right? So the chloride ion is formed as a result of a chlorine atom gaining an electron that would cause that imbalance where now you have more electrons than protons. So I'm just kind of like laying the groundwork here. That's how we end up with a chloride ion, right? We have a chloride ion that's negatively charged. How we ended up there was because the chlorine atom had gained an electron to cause an imbalance. So now you have more electrons than protons. Let me know if that's clear to you, because I'm going to show you now how we're going to go back to being an atom, because that's essentially what's happening, right? Okay, so Claude said that's clear, and I see those thumbs up. All right. So we have our chlorine, we have our chloride anion now, right? Now, what's happening at that anode is that chloride ion is then wanting to go back to that neutral state, or that's what's gonna happen. It's gonna go back to a neutral state now, right? But the way that it became an ion was because it had gained an extra electron. So to go back to the state of being neutral, it would then have to lose that electron that it had gained, right? So oxidation is lost. So it's going to lose that electron that it had gained to become that negative ion in the first place. And that's exactly what we mean when we say at the anode, oxidation, which is the loss of electrons, takes place. So it's going to lose that electron that it had gained, and it's going to go back to its native state where it's neutral. And that's that chlorine, that diatomic chlorine that's going to form that gas, right? So you might see, and you might be able to tell me right away that something is wrong with this, and that's that it's not balanced. So to balance it, we have 2 chlorine atoms over here. So we have to put a 2 before this. And then now we have a charge imbalance because the overall charge over here, what's the overall charge over here? Because this is a free state now, you know. It's just chlorine with chlorine, it's not ion. What's the oxidation state of the chlorine in this state? What's the oxidation number over here? 0. So let me just put a little 0 up here so we know that. And then over here, now, so if this is 0 over here, the overall charge over here must also be 0 when we put everything together, right? So we have 2 negative charges here, and it's losing the 2 electrons. So that would be, we need a 2 here for it to balance to get to 0, right? Does that make sense? So 2 negative charges, and it's losing those, so it's giving away those 2 negative charges to end up being 0. So we need a 2 to put the 2 here, and we need to put the 2 here because we have 2 chlorine atoms over here. So to make it perfectly balanced, that's what we do, right? So this is what that half equation at the anode would look like, which is indicative of oxidation. Right? So oxidation is the loss of electrons. We have our chloride ion that's negatively charged. It's losing those 2 electrons, or it's losing that electron, but we have to balance it, so we end up with 2 there. And we get that Cl2 in its free state, its oxidation number of 0. So you can see that we're going from an oxidation number of -1 to 0. And that is an increase. If you're on the number line and you go -1, 0, 1, 2, let me put -2 here just so you can see it. That is actually an increase in oxidation number, right? You're going from -1 to 0. So that's also a secondary definition of oxidation. It's an increase in the oxidation number, but it's also, most importantly, a loss of electrons, right? So if we're all on the same page there, just give me a thumbs up so I know that you're still here with me and you're not completely lost. Let me know if that's good. I'm going to show you the one for the cathode now, but I want to make sure that this is clear and that nobody's being left behind. So give me those thumbs up and let me see if you understand that whole half equation thing that I just did and how that relates to oxidation and the ion that then needs to become a neutral atom again. Let me see those thumbs up if that's clear. Okay, so I see those thumbs up. I want to see more though. Is it that the people who aren't saying anything, is it that you're not there? Oh my gosh, why am I? Okay. Is it that you're not? Okay, let me check the chat. Half thumbs up. Ashani say half thumbs up. All right, Ashani, how will you have a full thumb up? Full thumb up. What's wrong?
Could you quickly go through it again, miss, please?
Which part? Which part of it? The equation?
Yes, miss, the half equation.
Okay, so okay. So what I'm saying here is that you have your chloride ion that's negatively charged, right? That's here, right? That's this. So because it's at the anode, we know that oxidation takes place at the anode, which is a loss of electrons. But the reason why, if you really think about it from a particular standpoint and the particles and what the particles are doing, is that you have your chloride ion that is, where's my thing? You have your chloride ion that's negatively charged, right? But for it to have gotten to that state, it had gained electrons, and that's why it have that negative charge, right? Because in its native state, it's like neutral, it doesn't have any charge. But because it gained an extra electron through that bonding, really, through bonding with sodium, then it gained that negative charge. Because now you had an imbalance, you have more electrons than protons, right? That's just like the bonding principle and how bonding works and so on. But what I'm saying is that the anode, when it gets to the anode where oxidation takes place, which is a loss of electrons, that's how it's going to get back to its native neutral state where the oxidation number is 0. So then we're going to say, oh, because the chloride ion is negative and it wants to come back neutral, it has to lose that electron that it gained that made it negative. So it's going to lose that electron to come back to chlorine, diatomic chlorine, because that's how chlorine is in nature. It's diatomic, so that's why we have the Cl2. You're never gonna see chlorine by itself, like Cl, just so. It's always Cl2, right? It's a diatomic gas in nature. So to get back to that diatomic gas where the oxidation number is 0, you have to, this has to lose that electron that it gained that made it negatively charged in the first place. Does that make sense?
Yeah, I'm following numbers.
Okay, and that oxidation, and that process is oxidation, which is a loss of that electron that it had gained that made it negative in the first place. Okay?
Yes, miss. Thank you.
But this isn't balanced, so let me put balanced again. 2 Cl and 2 because there are 2 chlorine atoms over here, and then 2 E here because the charges have to balance, right? So that's how that's balanced. All right. So similarly, we can take a similar approach for the cathode in our analysis and how we're thinking about it, right? So as I mentioned earlier, at the cathode, we have our cation that is moving towards the cathode. The cation is positively charged and opposites attract. So that means that the cathode is negatively charged, right? All right. So here we have our cation, that's Na plus. A cation is formed when we have more protons in the system than electrons. And that's because there was a loss of electron. That's why it got to that state, right? You know that sodium, it has that 1 electron, valence electron, and when it participates in any bonding event, it gives away that 1 to become stable and more like a noble gas. So when it gave away that 1, you had one less electron than proton. You had more protons in the system, in the nucleus, than electrons that were rotating around, orbiting around. And so it ended up having a positive charge. So that's why you ended up getting Na plus in the first place, right? All right, so we have Na plus. We have an Na plus. That's that ion now. That's that cation, right? We want to go back to the state where we're neutral though. We want to go back to that neutral state right now. And that's gonna happen when reduction takes place, which is it gaining back that valence electron that it lost in the first place to become Na plus. Do you see where I'm coming from? It's Na plus because it had given away that 1 valence electron to participate in bonding. But
Yes,
now we're saying we want it back. Give me back my electron. Give it back to me so I can be neutral again. So that's reduction. Reduction is gain, right? And that's taking place at the cathode. So we have the Na plus, and he's saying, give me back my electron. Give it back to me. Give me back that 1 that I lost so I can be neutral again. So it's Na. It's a solid, and the oxidation state now is 0, and it's going from that to that, right? The charges are all balanced, plus, minus, it goes to 0. So now we're going from, if we look at our number line, wait, what am I? Yeah, if we look at our number line now, we're going this way, right? We're going from 0, we're going from 1 to 0, from +1, let me put the plus here. We're going from +1 to 0, so that's reduction, right? I'm doing all this to just show you all the different ways that you can keep track of what's going on in your head. That's why I'm all drawing this number line stuff. That's reduction because we're going backwards on the number line. There's a reduction in that oxidation number from +1 to 0. And then in the case of the chloride, and we were going from -1 up to 0, that's an increase in oxidation number. So that's oxidation. So that's another definition. That's one way of looking at it as well. But let us get comfortable with the definition that we said is most important, which is this. Oil rig, right? Okay, so just to recap, oxidation is loss, reduction is gain. At the anode, we are, the anion is losing the electron that it gained that caused it to become negatively charged in the first place. And that loss is oxidation. And so when we lose that, we go back to our oxidation state of 0. And in this particular case, we're becoming our neutral chlorine diatomic gas again. At the cathode is where the cathode is negatively charged. The cations are going towards it because the cation is positive. The cathode is negative. So the cation is going towards it. The cation, in this particular case, it's sodium, the sodium ion. That sodium ion is positively charged because it had given away its valence electron to participate in bonding, ionic bonding with that chlorine. But now it's saying, give me back my electron that I gave you. And that's exactly what that chloride ion is doing. Because if you look at it this way, you have to think of it as a balancing act now. Now the chlorine is like, okay, I'm losing, I'm giving it back to you. I'm giving you back your electron. I'm losing it, I'm giving it away back to you. And sodium is like, thank you very much. I'll take it back. I'm gonna take back my electron. And that's exactly what sodium does right here. The sodium ion, it takes back its electron and it becomes sodium, neutral sodium. And chlorine is like, all right, take it back. I don't want it neither, take it. So it loses it and it becomes chloride ion again. Does that make sense? Thumbs up, thumbs down, yes, no, maybe so. All right, so that makes sense to you guys. So then you should be able to do this for most of the cases then going forward. There are a few ones that are like you really have to just remember what the half equation is, because there are some tricky ones, particularly when you have solutions, right? When you have like the hydroxide one, like it's kind of hard to sit down and rationalize it like I just did here to come up with these half equations on the fly, right? So there are cases in which you directly have to remember what the half equation is. And I like point you to what those ones might be. But for the most part, you can always do a similar analysis like I just did here to figure out what the half equation should be, okay? So if we're all good on here, I'm gonna go ahead and clear the slide. So make sure you ask your question now or forever hold your peace, because we're gonna increase, we're going forward now. So if you have any questions on this one, let me know right now, because I'm gonna clear the screen and move forward. So if there are any questions that remain in your head about this stuff, speak now or forever hold your peace, okay? All right, I'm clearing it. All right, so now we're at this idea of an electrochemical series and electrode products, right? So we're like trying to figure out what's gonna get formed at the electrode, right? Given all the complex and intricate structures or solutions that we can have, what's gonna be your electrode product? Like just now, let me just back up. Just now when I did this was fairly straightforward, right? And it was fairly straightforward because we had inert electrodes, which we said weren't gonna participate in the reaction. So it's not gonna complicate anything. They're inert, they're not gonna mess with anything from a chemical reaction standpoint. We have molten sodium chloride, and molten just means that there is no, it's not aqueous. There are no ions from any water in it. It is what it is. It's just a chloride ion, that's your negatively charged species, and it's a sodium ion, that's your positively charged species. That's it. This is like as basic and as simple as you can get. When you have this, you can just do an analysis from the standpoint of, oh, of course, this is the cation that's going to go towards the cathode and get discharged. And by discharged, we mean loses an electron or gain an electron. You just, whatever the reaction is. The discharge just means that is the ion that's going to undergo a change, right? So it's clear to us, we know straight up that the sodium that's going to go towards the cathode. There are no other anions there are no other cations to compete with this for the cathode. And similarly over here, there are no other anions to compete with the chloride ion for the anode. So that's what we mean. There's no competition here. We know what's going to happen because it's molten NaCl. There's no water in it to contribute its own ions. Even though water is only weakly ionized, it still has ions that could potentially compete. But in this case, because it's molten NaCl, it's not going to compete, right? All right, so that's where, when we have a competition, just keep that in mind. Whenever we have a competition of ions, that's typically stemming from either your electrodes are not inert anymore, they're active, and you have copper that's gonna like throw you off, or you have an aqueous solution, which means that the stuff is now dissolved in water, and water is gonna contribute its own ions that could then compete with the ions in the electrolyte in and of itself. Then we have to be able to think about now what ion, well, which ion is gonna get to the cathode? Which ion is gonna get to the anode? Because now we have multiple anions and now we have multiple cations. So which one, right? So the electrochemical series is a way of guiding you into figuring out which ion is gonna win, essentially. And then along those same lines, then you'll be able to say what's gonna be formed at your electrode, right? Because if it's not the chloride ion that's gonna get discharged, and you're not gonna get chlorine gas, you're gonna get something else, right? Because nothing is gonna happen to that chloride ion because somebody else win him. Somebody else compete with it and beat it out and got to and was able to then get oxidized at that anode, right? So that's what we mean by electrode products. So here's our electrochemical series. And the electrochemical series just tells us a tendency of a cation or anion to discharge relative to the other ones that are present, that would potentially be present in that aqueous solution, right? So we have on the left our cations, and then we have on the right our anions. And that's because those are the species that are mobile and would then be able to move throughout the electrochemical cell. The cation would be moving towards the cathode, the anion will be moving towards the anode. But if we have one mix-up and blender where we have hydroxide ions and we have chloride ions, and so for example, from a cathode standpoint, from a cation standpoint, we have lithium and we have the H+, you have to know which one is gonna get preferentially discharged at the cathode or at the anode, right? And so what the electrochemical series does is essentially what it's saying is that the lower the cation is or the lower the anion is, all right, whichever one is lower, that's the one that's gonna win. So if I am choosing between the chloride ion and the hydroxide ion is gonna win, meaning this is the one that I'm gonna have to write the reaction at the anode for, because this is the one that's gonna get oxidized. If I have, similarly the cathode, if the ions in my solution, the cations in my solution are sodium and H+, so that's from a aqueous solution standpoint, guys. That's if I have, say, sodium. Say I have sodium chloride. Let me just write it out real quick. If I have sodium chloride and I dissolve that in water, that's an aqueous solution, right? That's an aqueous solution, and that's when the mix-up and blender come, because now, as far as water goes, water has its own ions that, even though it's weakly ionized, it has its own ions that are gonna come from it, right? And so from a cation standpoint, we're gonna have H+ from the water, and from an anion standpoint, we're gonna have OH-. And then from sodium chloride, we already established that the ions that make that up are the Na+, and then the anion is the Cl-. So here's a competition now. The competition is from a cation standpoint. we're choosing between whether sodium chloride is gonna win or H plus is gonna win. And from the anion standpoint, we're saying, oh, is it chloride, the chloride ion that's gonna win out, or is the hydroxide ion gonna win out from the water, right? And what the electrochemical series does is it tells you that whatever one is lower is the one that's gonna win. So for sodium chloride, for aqueous sodium chloride, what's gonna win? It's gonna be, it would be this because that's lower, and then it would also be this because this is lower, right? So there are two examples that you have to study in particular, keeping in mind that this is how you do the analysis, right? You write out all your cations and you write out all your anions, and you use the electrochemical series to decide which one is gonna win. But while we're here, I want you guys to know that there are particular cases, there are other factors that determines which cation win. It's not just about the position in the electrochemical series. There's also the concentration of the species, specific species in the solution matters. And then of course it matters whether we have an inert electrode or an active electrode. So I'm not sure if we'll be able to do these two examples today because I want to get to calculations, which I don't know if I'll be able to get to. But what I will say is that you should know and be very comfortable based on the syllabus for CXC. You should know, study the case in which you have dilute sodium chloride being electrolyzed versus concentrated sodium chloride being electrolyzed. Because as I mentioned just now, it's not only the electrochemical series that determines which of these ions win, it's the concentration as well. So if we're saying that we have concentrated sodium chloride, that means that we have a lot of sodium ions and a lot of chloride ions. And so whereas in this case, the sodium ion and the chloride ion lost out, it might not be the case if you have a concentrated solution of sodium chloride, right? So in that case, the concentration would trump the position of the ion, and that's what you'd pay attention to. So just like keep that in mind. Let me see. So just make sure you're comfortable with those examples, because yeah, it's not, you have to balance, or you always have to balance the different factors. And there are three factors: the position in the electrochemical series, the concentration of the ions in the electrolyte, as well as whether you have an inert or active electrode. And that part is like not too bad, because if it's inert, you don't have to worry about it. But if it's not inert, you have to think about what ions actually make up the electrode that could then compete with these, right? So maybe what would happen is, so you have, well, let me not jump the gun, but like you might have a copper electrode and the copper has its own ions too, or you have the copper that's a solid and that might want to become reduced. It might be energetically more favorable, which means that it would take less energy for you to just reduce the copper or oxidize the copper, whatever the case may be. And when you do that, in that case, the copper would win. So just to not confuse you, just to bring it back here, what I'm saying is the electrochemical series can guide you when you have competing ions as to which one is actually going to get discharged, which one is going to win. You also have to pay attention to whether it's a concentrated solution, because if you have concentrated solutions, that means that you have more of one ion than the next, in which case the one that you have more of will win, right? So I'll just leave this at that for now, but let me know if you have any questions on the electrochemical series in general. So Jamar said, Miss, wouldn't hydroxide be discharged in only in a dilute solution? Yes, that's exactly right, because no, not only is it that hydroxide is below is below chlorine in that solution, now you don't have as much chloride, period. So the chloride is not going to be able to compete, period, right? So you have two things stacked against the chloride ion in a dilute solution. It dilutes, which means you don't have that many chloride ions to begin with, but also the hydroxide ion is lower than it in the electrochemical series. So the hydroxide ion is what would get discharged, and that's what would get oxidized at the anode. Right? Does that make sense to you, Jamar? Is that your question? Let me see if there are any other. Are there any other questions? Does that make sense?
Yes, ma'am.
Okay. Are there any other questions on this? Let me know if there are any other questions on this. Or if this is all clear, what this idea of the electrochemical series and why we care about the electrochemical series, period, right? If there are any questions, let me know. If it is clear, give me a thumbs up and I'll move on to our next slide. I'm looking for those thumbs up, so please let me know what your position is on this. If it's clear, if it's not clear, let me know either way. If you don't sit there and not know what's going on, right? This is not the place for that. This is not the place that you come to not know. This is a place that you come to know things, right? And leave knowing things. So, okay, so that's this idea of the electrochemical series. And as I said, my homework for you or my assignment for you is to take your textbook. And I hope that you guys all have textbooks and you're not just using the concise revision. That's good. That's great. But you should have a reference textbook. Make sure that you go, or even go on YouTube and type in electrolysis of dilute sodium chloride versus the electrolysis of concentrated sodium chloride, and convince yourself that what I'm telling you is actually so. Just look at it and think of it and be like, okay, now I understand. I have more clarity. If it is that you need more clarity, even if you think that you're 100% clear on it right now, still go to YouTube and type that in, right? Electrolysis of dilute sodium chloride, electrolysis of concentrated sodium chloride. I really encourage you guys to do this because this is something that I have seen on past papers before and it could come up, right? So make sure that you pay attention to that. Even if it doesn't come on a paper 2, it might come on paper 1, in that you have to know the difference between them. What's gonna get oxidized versus what's gonna get reduced. Like, you have to know that. So pay attention to that, okay? So let's see where we are now. We have 10 minutes, guys. We have 10 minutes now. So let's see. Maybe I'll skip the example stuff because I feel like examples are things that you guys can kind of do on your own and just kind of read them and make sure that you know them. Whereas I want to help you with translating what we just learned to calculations and to see how those actually manifest themselves. So like what we just discussed in a calculation and how you would even begin to set up a calculation. So let me see if I can jump ahead here. You guys can look up these examples in your own time. And I told you about this. Electrolysis of aqueous sodium chloride. Pay attention to the concentrated and the dilute form, as well as pay attention to I'll look this one up too. The electrolysis of aqueous copper sulfate. Please, guys, let me check them, let me mark them so you know that you remember that I said to look these up. Look up this and look up this. Like, these are important too. So if you have time, definitely look these up as well. But I would say for sure, for 100%, make sure that you know these two bottom ones, because that's where the trickery comes in, where you can get tricked, right? From the standpoint of the electrochemical series being important, as well as the idea for aqueous copper sulfate in particular, for this idea then of the active electrode, when copper is an active electrode that's often used. I want you to look at this example so you can see how the copper can actually compete with the ions in that solution, and it will then change your electrode products. You won't get what you would think that you would have gotten if it were inert. So pay attention to these examples for sure in your own time, okay? So let's see where we can get as far as the calculations go. I think I might have to do this the 27th again. I'll have to finish it because I don't know if I'll finish it today. And as I always say, guys, like honestly, like I would very much rather finish these series of free classes knowing that I taught you two things very thoroughly. And from the looks of it right now, it's looking like those two things that I can confidently say that I really taught you thoroughly, and you should have a very good grasp of. Those two things would be the mole concept and electrochemistry. And I think that if you have a good grasp of that for the most part, the other things you can fill in. So I think what we're going to do is we're going to see how far we can get in electrolytes calculations, and then next time, not next week, 27th, we'll probably like do more of these, because there are a wide variety of electrolysis calculations that you can get and see. So I think I'm gonna spend the next 27 doing that. So I was thinking maybe tentatively of doing organic chemistry then, but I'm probably not. If you're gonna join us in April for the past paper sessions, I'll do past papers with organic chemistry questions in there. But I think I'll probably just like focus on rounding out electrochemistry, specifically the calculations next time. But I mean, it's my hope that so far what we've done today really laid a solid foundation for you, or a solid framework through which you can understand electrochemistry better. Maybe if you understood it before, that's great, but it may be even better than before based on how we did it today. So let's see, maybe I'll just check in here. Maybe I'll check in here with your understanding of the concepts that we've done so far today, like I always do, with you giving a ranking or a number from on the scale of 0 to 10, where you were versus where you are now. In light of the fact that I just said that let's do the calculations next time, or continue them next time, I won't rush to jump into it today, given that we only have like 7 minutes left. I'll just talk with you guys now. I'll talk with you guys now and hear your concerns or questions or what you think of the overall plan that I just shared. How about that? I don't want to be a dictator telling you everything, telling you what we're going to do. I want to hear from you guys. What do you think of the plan going forward? And also I want to know what your level of understanding is today, as far as the foundation or the basic principles, the guiding principles of electrochemistry are concerned. So talk with me now, guys. Let's just talk for the rest of the time, and next time I'll start this calculation stuff. So let me just stop sharing that so I can see all your names, because I can't see your beautiful faces. You can show me your faces now if you want. You can turn on your camera if you want and talk to me, or not. It's up to you. But I just stopped sharing that screen. I want you guys to engage with me now and let me know where your understanding is. So Jada said, boom, miss. I was at a 2 out of 10, and now I'm at a 10 out of 10. So that's what Jada said, and I'm very happy to hear that, Jada. Very happy I could be of any help to you. And next time we'll do the calculation. So we'll really put that new understanding to work, that new fundamental understanding to work when we do the questions next week. So you will have opportunities to write your half equation at the anode. At the cathode, you'll then choose which one is going to get preferentially discharged based on the position in the electrochemical series. Is it an inert electrode or an active electrode? Is it a dilute or a concentrated solution? Like, we'll get a lot of practice with that for the 27th of March. But today we did what I think is a very solid, basic, basal, fundamental electrochemistry stuff that you need to know and understand why things happen the way that they do. And so I just want to check in to see where you guys are. So Jamar said we have memorized Electrochemical Series. I don't think so, but I think it would be good to just know the frequent occurrences or okay, so the examples that I told you to look at, like if you do those examples, you kind of will be, and you do enough practice problems, it will be ingrained in you as to what comes before what. Like you know, OH minus is at the hydroxide is at the bottom, hydrogen is closer to the bottom. Like you just kind of know those things. I don't think you have to memorize it. If you can and you have memory space, go for it. Or if you have photographic memory, just look at it and take a picture in your head. But like I would just say, dude, by doing problems and doing examples, enough examples, you will be able to be quite confident in selecting which ion is going to get preferentially discharged. So that's how I would answer that question. So Aquila said she's from a 0 to 8. I'm happy to hear that, Aquila. And if there are any specific questions that you have as to how we can get you to a 10 before next class, now is the time to ask me, and then, or maybe we can speak further offline. You can email me and I can talk to you via email or voice note or whatever to clarify that, since we're coming to a close here. But let me know what's the difference between that 8 and that 10 for you. Is there anyone else that wants to share how they feel from an understanding level standpoint, where you were before and where you are now? Because next week we're gonna just dive into calculations, right? Of course, I will be explaining concepts as we go throughout it, like why is this and why is that versus that. But like the amount of time that we spent on concepts today, we're not gonna do that next time. We're gonna do calculations, which is like, I have a lot of questions. I have a lot of electrochemistry questions for you guys, like a lot. And there are levels to it, right? You have singly charged ions and triply charged ions, and those behave differently in terms of the amount of electricity that's gonna carry and how much product is gonna produce. There are levels to it. So I have a lot of questions. So I think it's good that it's a good idea to do that, to dedicate an entire class to that next week. Not next week, the 27th. So what do you guys think about that plan? So we're not gonna do organic chemistry. We're gonna spend our time and really nail down electrochemistry. So let me know what you guys think. Hands up if that's good. Hands down if you're like, Miss, we want organic chemistry. Come hell or high water. We have to do organic chemistry. Let me know what you're thinking. If that's okay. If it's not okay, unmute and tell me, say, Miss, it not gonna work. All right, Claude says yes. Kayla says yes. Who else says yes? Who else says that that's okay, that you really want to, Jamar, you really want to nail this electrochemistry stuff? Because like even your, I think that there are a lot of SBAs that are electrochemistry heavy, I've come to understand, right? And so I think that this might, I don't know if you submitted SBAs already, I don't know how that whole thing goes, but this session that we did today should be able to help you a lot with your SBAs, I think. Quantitative. Okay, so Ashani, so you need a calculation then. So we'll do the calculations next time, 27. So you'll see those. Yeah, cool. So that's where we are for now. And I haven't heard from everybody. I heard from most people that that's okay. But see, if you're here, since you're here, say something. We're at the end now, so we're gonna end the meeting now anyways, but I want to hear from everybody. Jabari just put his thumb up, so I see that he's okay with everything. If there are no further questions, if you're okay with everything, I will see you guys on the 27th of March, and then we'll do the calculations then, okay? All right, guys, so I'm gonna go now. It was a pleasure being here with you guys again. Thank you for showing up. Thank you for participating, and it's my pleasure. So I will see you guys on the 27th, which is not next Sunday, it's other Sunday, and we will do our calculations, okay? All right, guys, have a great week now. Bye.
Bye, Miss.
Bye.